Hello everyone. Today we will discuss about expected value of random variables. Before going to the details of expected value of random variables, let's have a quick recap. So we know that random variable is a function that maps the outcome of a random experiment to real numbers. So we have the sample space S. So we will map the outcome of the random experiment to say real numbers. So this is your real axis. This is your random variable. So we know that random variable is a function that maps the outcome of a random experiment to real numbers. Then we discussed about cumulative distribution function, and cumulative distribution function is represented as fx of x. So this is the random variable and this is the value taken by the random variable, and that is defined as probability that the random variable x takes a value less than or equal to small x, or the probability that the random variable x takes a value less than or equal to x. So this is the value taken by the random variable and this is random variable. So then we discussed about PDF, probability density function. So probability density function is defined for continuous random variables. So it is defined as, say, fx of x equal to differential of d by dx of fx of x, or this implies that CDF is defined as fx of x equal to integral minus infinity to x fx of x dx. So these are the things we discussed in the last class. So today we will discuss about the mean value of the random variable or expected value of the random variable. If x is a continuous random variable with a valid PDF that is defined as fx of x, then the expected value of the random variable x is given by expectation of x is equal to, so mu of x, which is equal to integral minus infinity plus infinity x into fx of x dx, where x is the values taken by the random variable. If x is a discrete random variable with a set of elements x1, x2, etc., xn, small n, and their corresponding probability is p of x1, p of x2, etc., p of xn, then the mean value of the random variable x is defined as expectation of x equal to summation of I equal to 1 to n xi into p of xi, where xi is the value taken by the random variable and p of xi is the probability of occurrence of that particular value. Now we will derive the mean value for binomial random variable. Usually, binomial random variable is represented as BNP, where n is the number of trials and p is the probability of success. Now, the probability of k success in a binomial experiment is given by probability that x equal to k is given by probability that x equal to k means probability that k success occur out of n trials. That is given by nck p raised to k 1 minus p raised to n minus k. Right. So this we discussed in the last class. Today we will discuss the mean value for binomial random variable. So in binomial experiment, the value of k can take any value from 0 to n. Right. So by definition of mean value, so we can write it as expectation of x equal to sigma k equal to 0 to n k into probability that x equal to k. Expectation of x equal to sigma k equal to 0 to n, that is the value taken by the random variable is from 0 to n, k into probability that the random variable takes the value k. Right. Okay. We know that probability that x equal to k is nck p raised to k 1 minus p raised to n minus k. Let 1 minus p equal to say q. Now probability that x equal to k equal to nck p raised to k q raised to n minus k. Right. Now Now expectation of x can be written as sigma k equal to 0 to n k into nck p raised to k q raised to n minus k. So this can be written as sigma k equal to 0 to n k into nc. What is nck? N factorial by n minus k factorial into k factorial into p raised to k q raised to n minus k. So this can be written as sigma k equal to 0 to n k into n factorial divided by k into k minus 1 factorial into n minus k factorial into p into p raised to k minus 1 into q raised to n minus k. So this k cancel, and this can be written as sigma k equal to 0 to n np into this n factorial can be written as n into n minus 1 factorial. N minus 1 factorial divided by k minus 1 factorial into n minus k factorial into p raised to k minus 1 q raised to n minus k. And in this case, so this can be written as, so in this case the value of k equal to 0 is not valid. Now this can be written as np in sigma k equal to 1 to n minus 1 c k minus 1 p raised to k minus 1 q raised to n minus k. Right. So this will be equal to np into, so we know that this can be written as p plus q the whole raised to n, right? So hence it is called binomial distribution, right? So that is p plus 1 minus p raised to this n minus 1. So this n minus 1. P plus 1 minus p raised to n minus 1. So this will be equal to 1. Right. So expectation of x can be written as, expectation of binomial distribution is given by np. Now we will find the mean value for Poisson distribution. We know that in Poisson distribution, probability that x equal to k is given by e raised to minus lambda, lambda raised to k by k factorial, and where k takes a value ranges from 0, 1, 2, 3, etc. up to infinity. Right. Now we will find the mean value for this Poisson distribution. Now we know that expectation of x equal to sigma k equal to 0 to infinity k into probability that x equal to k. Right. So this can be written as sigma k equal to 0 to infinity k into probability that x equal to k is e raised to minus lambda, lambda raised to k by k factorial. So this can be written as sigma k equal to 0 to infinity k into e raised to minus lambda, lambda raised to k by k into k minus 1 factorial. So k cancel. Right. So this can be written as, so I am writing lambda raised to k as lambda into lambda raised to k minus 1. So this can be written as lambda into e raised to minus lambda into sigma k equal to 1 to infinity lambda raised to k minus 1 by k minus 1 factorial. Right. Now what is this? This is the definition for e raised to lambda. So this can be written as lambda into e raised to minus lambda e raised to lambda. So this can be written as lambda. So expectation of x for Poisson random variable is, or mean value of Poisson random variable is lambda. Now coming to Poisson approximation of binomial distribution. We already discussed about Poisson approximation of binomial distribution. Today I will give a proof for this Poisson approximation of binomial distribution. The Poisson distribution is a limiting case of binomial distribution under the following condition. One is the number of trials n is indefinitely large, that is n tends to infinity. Second is the probability of success for each trial is small, that is p tends to 0. And third condition is the product of number of trials and the probability of success np should be a constant and is finite. So if these three conditions are satisfied, we can approximate the binomial distribution as Poisson distribution. Now we will look at the proof for Poisson approximation of binomial random variable. So let x be a binomial distributed random variable. That is, probability that x equal to k can be written as nck p raised to k 1 minus p raised to n minus k. Right. So this can be written as n factorial by n minus k factorial into k factorial into p raised to k 1 minus p raised to n minus k. So which can be written as n factorial can be written as n into n minus 1 into n minus 2 into etc. up to n minus k minus 1, that is n minus k plus 1 into n minus k factorial divided by k factorial into n minus k factorial into p raised to k can be written as, so we know that np equal to lambda, right? So p can be written as lambda by n. So lambda by n the whole raised to k 1 minus lambda by n the whole raised to n minus k. Now this n minus k cancel. Now I am taking n as common factor. So how many n can be taken? So this 1, 2, 3 etc. K minus 1, right? So 1, 2, 3 etc. up to k minus 1 plus this one. So total n raised to k. So total k n's are taken outside. So that can be written as n raised to k into 1 minus 1 by n into 1 minus 2 by n etc. 1 minus k plus 1 by n into lambda raised to k by n raised to k 1 minus lambda raised 1 minus lambda by n the whole raised to n minus k divided by k factorial. So n raised to k cancel. Now as n tends to infinity, so this becomes 1, 1, 1. So what we left is, this can be written as n tends to infinity, so this term becomes 1. So what we left is lambda raised to k by k factorial into, that is as n tends to infinity, 1 minus lambda by n the whole raised to n divided by 1 minus lambda by n the whole raised to k. Again this will becomes, as n tends to infinity, this becomes 1. So what we left is lambda raised to k by k factorial 1 minus lambda by n the whole raised to n. So we know that limit n tends to infinity 1 plus 1 by n the whole raised to n can be written as e. Then limit n tends to infinity 1 minus lambda by n the whole raised to n can be written as 1 minus or 1 plus 1 by n the whole raised to n into minus lambda. So as n tends to infinity. So this we know that e. So e raised to minus lambda. So limit n tends to infinity 1 minus lambda by n, the whole raised to n is e raised to minus lambda. Right. Or in other words, we can say that we know that e raised to minus x is 1 minus x. We use this property here. So anyway, we will get it as limit n tends to infinity 1 minus lambda by n, the whole raised to n equal to e raised to minus lambda. So equation A becomes, A gives probability that x equal to k as n tends to infinity is lambda raised to k by k factorial into e raised to minus lambda. So as n tends to infinity, binomial distribution is approximated as Poisson distribution. Thank you.